The automotive world is changing rapidly. According to forecasts, by 2030, 23 million people in the world will become happy owners of electric cars. General Motors has announced plans to stop selling gasoline-powered vehicles by 2035. Audi's goal is to close their production by 2033, and many other major automotive companies are following suit. By 2040, 2/3 of global passenger car sales will be electric vehicles, according to Bloomberg NEF. While this may seem like the ideal path, there is one big problem. Currently, electric vehicles and powerful batteries typically use lithium-ion batteries for energy storage, which are difficult to recycle. As the world seeks to electrify vehicles and store renewable energy, a major question looms. What will happen to all the old lithium batteries? By 2040, 5,750,000 tons of these will be decommissioned. This sets the task of improving technologies and increasing the capacity for recycling batteries that have exhausted their resource. After all, if the current trends in the handling of used batteries continue, most of them may end up in landfills, with all the ensuing problems for the environment. But these power supplies contain valuable metals and other materials that can be recovered, processed, and reused. Battery experts and environmentalists give a long list of reasons to recycle lithium-ion batteries. The recovered materials can be used to make new batteries, reducing manufacturing costs. These materials now account for more than half of the cost of a battery. Priced for two common cathode metals, cobalt and nickel, the most expensive components cost roughly $27,500 and $12,600 per metric ton respectively in recent years. In many types of lithium-ion batteries, the concentrations of these metals, as well as lithium and manganese, exceed the concentration in natural ores, which makes spent batteries look like highly enriched ore. If these metals can be recovered from used batteries on a larger scale and more economically than from natural ore, the prices of batteries and, by extension, electric vehicles should fall. However, the share of recycling in the disposition of lithium-ion batteries is very small today. In Australia, for example, only 2 to 3% of lithium-ion batteries are collected and sent for recycling. The recycling rate in the European Union and the US is not much higher, less than 5%. There are many reasons why recycling of lithium-ion batteries is not yet an accepted practice, says Linda L. Gaines, Transportation Systems Analyst at Argonne National Laboratory. Reasons include technical constraints, economic barriers, logistics issues, and gaps in legislation. Another reason is that the most widely used battery methods of recycling of previous technologies, such as lead-acid batteries, do not work well with lithium-ion batteries. The latter tend to be larger, heavier, much more complex, and even more dangerous if taken apart incorrectly. In a typical battery recycling plant, battery parts are ground into powder, and then the powder is either melted down, pyrometallurgy, or dissolved in acid, hydrometallurgy. But lithium-ion batteries are made up of many different parts that can explode if not taken apart carefully. And even when they are disposed of in the appropriate way, the resulting products are not easily reused. As a result, the process of recycling lithium-ion batteries is more expensive than mining more lithium to make new ones. Most recyclable batteries are subjected to high-temperature melting and extraction, a process similar to that used in the extractive industries. Those operations that are carried out at large commercial facilities, for instance in Asia, Europe, and Canada, are energy-intensive. The construction and operation of plants are also costly and require sophisticated equipment to handle harmful emissions from the smelting process. And despite the high costs, these factories are not recovering all the valuable battery materials. While the extraction of these metals requires huge resources. For instance, it takes 2,273,000 liters of water to mine 1 ton of lithium. In the Atacama salt flats in Chile, lithium mining is associated with a decrease in land cover, higher daytime temperatures, and increased drought in areas of national reserves. Therefore, it is essential to preserve metals when disposing of lithium-ion batteries. Logistical problems such as collection and transportation also hinder the widespread adoption of LIB recycling. Calculations show that in most cases, LIB recycling remains uneconomical, and profitability is achieved only under a very narrow set of chemistry, site, and process conditions. Let's look at an example. Based on the cost of transporting 8,000 tons of cells, still in batteries, from a collection point in the UK, the contribution of transport to the total cost of disposal is 7 to 13% for China, South Korea, and the USA, depending on the method of disposal, and about 2% for Belgium and UK. When implementing the transport fees specified in Everbat, the share of transport costs is still increasing, up to 70% for China, 65 to 70% for South Korea, 50% for USA, 20 to 25% for Belgium, and 5% for the UK. Obviously, only disposal within the UK and direct NCA recycling in Belgium become profitable. Recycling abroad is unprofitable. The wide variety of package designs and chemical compounds of battery further complicates the problem. Given the relatively small number of end-of-life electric vehicles, transportation costs will remain high and profits low for a long time to come. And it also hinders electric vehicle and battery manufacturers from effectively recycling end-of-life batteries. Until now, much of the effort to improve lithium-ion battery recycling has been focused in a relatively small number of academic research groups, usually working independently. Nevertheless, things are starting to change. Driven by the sheer volume of depleted lithium-ion batteries soon to come from end-of-life electric vehicles and ubiquitous portable electronics, startup companies are commercializing new battery recycling technology. In 2018, Tesla Chief Technical Officer J.B. Straubel, while making batteries at their massive gigafactory near Reno, Nevada, thought, "Why not start a company that will extract metals from factory scrap and other used electronics, and then return ready-to-use lithium, cobalt, and graphite to them to make new batteries?" Later that year, while still at Tesla, Straubel founded Redwood Materials, a next-generation mining company near Carson City. Prices for battery materials such as lithium and cobalt have since skyrocketed. But Straubel has good news. After a year of operations, Redwood Materials can save tons of useful metals, and it is more cost-effective than normal mining. The company can now mine enough materials to produce battery packs for 45,000 electric vehicles annually. Trucks filled with batteries arrive daily at the company's Carson City plant. Once e-waste is sorted for recycling, Redwood uses a proprietary hydrochemical process to separate the various metals. Used batteries are subjected to heat treatment in furnaces. All of the resulting alloys then go through a chemical process to turn them into ready-to-use materials. Flammable battery electrolyte is allowed to ignite under controlled conditions without the addition of other flammable substances, and at the same time, no emissions occur. Basically, we chemically disassemble everything and then start separating useful materials and use them as building blocks for production, says Straubel. It's not just Redwood that sees battery recycling as a lucrative business. Their Canadian competitor, Li-Cycle Corp, has its own factories for the extraction of useful materials from used batteries and electrical waste. Its patented spoke and hub technologies use a combination of mechanical safe size reduction and hydrometallurgical resource recovery, specifically designed for lithium-ion battery recycling. With the help of the know-how of the company, all types of lithium-ion batteries are transferred from a charged state to an inert state safely and efficiently. Cathode and anode materials are processed into end products for the battery for reuse in lithium-ion battery manufacturing or other applications in the wider economy. Thus, it can be expected that recycling will reduce the cost of the battery, which in turn will affect the cost of electric vehicles, making them more affordable. What is more, the mass processing of LIB, as well as the transition to electric vehicles, will certainly have a positive impact on the planet's ecology. Processing companies are currently confronted with a significant difficulty. The lithium-ion battery recycling market is forecast to grow to $18.1 billion in 2030 from $1.5 billion this year. In 5 to 7 years, we should be able to recycle end-of-life electric vehicles at the same pace as they are produced today.